Okay, so for this video, we are going to be having a look at conservative and non-conservative forces. Now, this concept is not really in your syllabus. However, I do think that if you understand the difference between conservative and non-conservative forces, it does help you to understand work energy theorem a little bit better, and also helps you to just, I guess, have a better understanding overall of the concept. So that's what we will look at today. Cool. But before we do that, let's look at some questions. Same deal. Please pause the video, right? Attempt these questions yourself first. And then after you have locked in an answer, you can press play so you can have a look at how I think through these kind of questions. Okay. So first one, if you push twice as hard against a stationary brick wall, the amount of work you do is what? Well, the key idea here is it's stationary. If it's stationary, then that means that the displacement is going to be zero. And so therefore, the amount of work you do is going to remain at a constant zero. Next question is going to be, whoops, my mouse, where's my mouse? Yeah, there we go. Next question, the quantity half mv squared is, that's literally just a recall question. So half mv squared is the kinetic energy of the object. So answer is A. Next one, car J moves twice as fast as car K, and car J has half the mass of car K. The kinetic energy of car J compared to car K is, okay, so let's have a think through this. Right, so I have here, I want to compare the kinetic energy. So kinetic energy of car J is going to be equal to half times, in terms of the mass, car J has half the mass of car K. So mk over 2, half the mass, times the velocity is twice as fast. So 2vk squared. And that is going to give me half times let's you know what, let's take all the factors out. So all my factors I'm going to highlight in blue. So that's my factor there, that's my factor there. Let's take that out. So I have half times 2 squared, which is times 4. And then after that, I have my half times mk times vk squared. And so if I simplify this, that gives me 2 times. So this becomes 2 times. And then this red bit here is just kinetic energy of car K. And so it is 2 to 1. The answer is B. Okay. Next one, 500 kilograms elevator is pulled upward with a constant force of 5,500 newtons for a distance of 50 meters. What is the work done by the weight of the elevator? So let's draw a diagram. So I have my elevator here. That is 500 kilograms. That looks like 560. 500 kilograms. Constant force pulled upward with a constant force of 5,500 newtons, for a distance of 50 meters. And then they want you to find the work done by the weight force, right? Not this pull force, so not quite this one. They want the weight force. The first thing I have to do is, of course, calculate the weight force. That's equal to mg. Mass is 500 kilograms. G is 9.8. So that gives me some amount. And then I will calculate this at the end. And then they want the work done, right? So work done by G is equal to Fg time dot product with the displacement. In this case, again, my weight force is of course going to go down. The displacement is going up. And so the angle between the two is going to be 180 degrees, right? So that becomes 500 times 9.8 times displacement of 50. And then I have cos of 180 degrees. So that gives me a negative answer. And so by just virtue of, the fact that I have a cos of 180, I can pretty much eliminate A and C straight away. And so now you could say it's 50-50, but might as well just do the calculations. So 500 times 9.8 times 50 times cos of 180 gives me minus 245,000, or minus 2.45 times 10 to the 5 joules. Answer is B. Okay. Number 6. I have Matthew pulls his little sister Sarah in a sled on an icy surface, so no friction, with a force of 60 newtons at an angle of 37 degrees upward from the horizontal. If he pulls her a distance of 12 meters, what is the work done by Matthew? Okay, so let's see. Icy surface, force and an angle, full distance of 12. So I assume what's going on here is I have a sled looking like this. It's being pulled this way at an angle, and the angle is 37 degrees. The pull force is 60 newtons. And then the distance that they travel altogether, so displacement, is equals to 12 meters. So from here, my angle between displacement and distance is just the 37 degrees, right? So if you have a look over here, in blue is my displacement over there. And so the work done by Matthew is going to equal to the force that Matthew applied, dot product with my displacement. That gives me 60 times 12 times cos 37. And so that's going to equal to 575.01. So let's just go 575 newtons. Okay. So that is how much, oh, not newtons, apologies. It is going to be in joules because it's work. There we go. Don't make the same mistake I did. There we go, joules. Okay. Question number, or next one. Is it possible for a system to have a negative potential energy? Yes, we've seen it before, right? And the reason why you can have negative potential energy is because I can have an arbitrary starting point, right? The choice of my zero level can be anywhere I want. And so by that logic, of course, I can have a negative potential energy. Okay, next one. An object is released from height h above the ground. A second object with 4 times the mass of the first is released from the same height. The potential energy of the second object compared to the first. Well, we know that potential energy is equal to, so let's go, potential energy is equal to mgh. And so if I have 4 times the mass, right, that means the potential energy is going to be 4 times as much as well. So that's D. Next one, 15 kilogram object is moved from height 7 meters above the floor, above a floor, to a height of 13 meters above the floor. What is the change in gravitational potential energy? I don't really care where the floor is, right? The floor doesn't have to be at the ground, because again, I can set my zero energy point anywhere. And so let's say my floor is here. Sorry, I'm just going, you know what? Let's just do it this way. I'm just going to set this 7 meter above the floor as my, so this is 7 meters. This is my zero potential, right? And so then I'm now going to move from 7 meters up to 13. So I need to work out the height difference, right? So this here is 13 meters. And so my height difference here is going to be 6 meters, right? So increase the height of 6 meters. And so now my change in potential energy, or gravitational potential energy, is just going to be equal to mgh. M is 15, G is 9.8, and then H is 6. If I put that into my calculator, 15 times 9.8 times 6 gives me 882 joules. There we go. Okay, so that's the change in gravitational potential energy. Again, very arbitrary. Where I can set my 0 point, right? So this is an example. You could, of course, do like mg, like if you set the ground as 0, you could work out the potential energy at 7 meters and then potential energy at 30 meters and then subtract them, but you end up with the same answer pretty much. Okay. Next one, or last one. 400 Newton box is pushed up an inclined plane. The plane is 4 meters long and rises 2 meters if the plane is frictionless. And an important point here that the plane is frictionless. So there's only the push force and the force of gravity acting on it. So how much work was done by the push force? Okay, so the work done by an external force, so in this case by an external push force, if you remember to our potential energy video, that's just equal to the change in potential energy, right? And so my change in potential energy in this case is just mgh. So that's equal to change in potential energy. And that's going to equal to mass of, oh, I already have my mg. Mg is 400, right? Because that's a 400 Newton box. So that's my weight already, times the height. I don't care how long the plane is because, again, it's frictionless. Right. Yeah, frictionless. And so really I only care about the how much it rises by, because again, potential energy depends only on the height, right? So times by 2, that gives me 800 joules, which is my work done by the external force, right? If you are unsure about this, please do go and watch the video on potential energy again. The logic of, in order for me to, lift up an object, an external force or external work has to be done on the object. And then by doing so, I've now stored some energy inside this object, which we call potential energy. And so if I calculate my potential energy difference, then that's equivalent to the external work that was done on the object. Okay. Cool. So that's the questions. Now, whoa, okay. What happened here? All right, you know what? It just went blurry all of a sudden. Let me pause the video and fix this up. Okay, that's hopefully now fixed. I don't know what happened there. But let's talk now about conservative forces. Okay. So conservative forces, the definition for it is this: all conservative forces have the following two equivalent properties. So these two things, point number 1 and point number 2, are equivalent, right? They are the same thing, just worded in slightly differently. So the work done by a conservative force on an object between any 2 points is independent of the path taken by the object. We've heard this term before in the previous video on gravitational potential energy, right? So it's path independent or independent of the path. I'll explain more detail what this means in a second. Or secondly, right? So again, both of these are equivalent. So another way to phrase it is that the work done by a conservative force on an object moving through any closed path equal 0. Okay, what do I mean by a closed path? Well, a closed path just means if I make a loop with the object. So if I start from here and I travel, make it go, let's go, where should I do it? It's not enough space. Okay, closed path essentially just means if I start here and then let's say I do some kind of loop over and then I start back at the same point, right? That now becomes a closed path, right? So I start from one point, go around, and then eventually end up back at the same point. And a conservative force, right? So a work done by a conservative force says that if an object goes around in closed path, then the work done has to equal to 0. So that means all the work has to cancel out so that at the end, the net work is equal to 0. Okay. And if the force doesn't have either of these two properties, so again, they're equivalent, but like if they don't have this property, then it is considered to be a non-conservative force. Okay. Okay, great. So let's have a look then in terms of path in a little bit more detail. So if I have an object starting at a given point, and then yeah, if it returns, so in this case, I have here not a same point, right? So I go from A to B. So this is point A, this is point B. Being path independent means that it doesn't matter whether I choose path A, so the direct path here, or if I kind of choose the curved path, path 2 over here, or path 3 around here. The work done by a conservative force in all of these three paths would be equivalent. So it doesn't matter which path I take, right? Because a conservative force pretty much only depends on the position of the object. Okay. If, however, it is a non-conservative force, then the work done at these different paths would be not equal. So now it depends on the path. Right. And you can probably now start to see too that like, yeah, it is equivalent to the second statement here, because if the paths are all equivalent, then going one way and then kind of coming back, it should kind of cancel out, and so it should all become zero. Okay. Um, okay. Yeah. Okay. Uh, so conservative forces do no work in a closed path. I think I should probably write it down. So conservative forces do no work in a closed path. And I will prove that to you with gravitational force in a second. Okay. Okay. If you push a crate across the floor from one point to another, the work that you do now will depend on which path you take, right? Whether the path is a short path between, the shortest path between point A to point B, or whether you take a longer curved path, right? Because, well, you can just imagine it, right? Like, is it easier for me to push a box from one point to another point in a straight line, or to go around in a curved line? Of course, the shortest path would be less work for you, right? Why? Because of friction, right? Friction is acting for that situation. So if you push the crate, let's say, according to like path number 3, right? So now you're taking like a more curved path. Now you essentially have you have to do more work against friction than if you were to push it along path number 1, right? So along a straight path. And so because of that, we say that friction is an example of a non-conservative force. Right. So this table here shows you a little bit of a list of different examples. So conservative forces are things like gravitational force that we talked about last video. Elastic force is a conservative force. Electric force is also a conservative force. Really, if you think about it, conservative forces are the weird one, because most forces are actually non-conservative. So things like friction, air resistance, tension in a cord, the motor pushing, or any kind of push force, pull force by a person, they are all non-conservative because they all depend on the path, right? So if I take a longer path, friction will act more. So there'll be more friction acting, right? If I take a longer path, there'll be more air resistance acting, and so the work for different paths are not the same. Whereas something like gravity, right? We said that gravity only depends on the position, so that means that gravity is an example of a conservative force, and there's only very, very few of these guys, right? So these are more of the special case. And then friction and all of those things, those guys are more of the norm, right? So most forces are non-conservative. Okay, so I'm now going to show you that gravitational force is a conservative force, right? So let's try it out. I'm going to add a page just so we have an extra working space. So to show that gravitational force is a conservative, I'm going to do the loop method, because I think the loop method is more fun. So let's say I'm standing here. So this is a person. This is me, right? I am carrying a rock, right? And I'm going to, so this is the ground. So this is my bumpy ground. I'm going to move this rock so that it is going up this way, and then it's going to go this way, and then it's going to go down this way, and then it's going to go back to its original spot this way. Okay, so I'm forming a loop. Now, the reason why I'm making a square loop is because I can't be bothered doing circular loop. Square loop works. So, like, look, if you want to challenge yourself, try prove this using a circular loop. It's not that much harder. It's just requires like 2 pi r and all that. Okay, so let's say that all of these slides are the same. So let's say I'm moving it at a displacement x here, x there, x here, x there, right? So let's call this x1, this x2, this x3, and this one x4. So if I want to work out the network, so work net acting on this ball, then yep. So the network, right, done by gravity in this case, is going to equal to. So let's talk about yeah. Sorry. Apologies. Had to pause video there for a second. Okay. So instead of network, let's just call it the work done by gravity in each path here. And then I'm just going to sum up all the work done by gravity at different points, right? So the ball, right, the gravitational force is always going to act down, right? No matter where the ball is, gravitational force is always down. And so here you can probably see that the work done, so let's call this work 1, this is work 2, this is work 3, and this is work 4. So the first leg of the journey, right? My work done by force of gravity is just going to equal to Fg dot my displacement, which is x1, right? And that is going to be equal to minus mgx, right? Because again, the angle between them is 180 degrees, so that becomes minus mgx. Now, what is work number 2 going to equal to? Well, work number 2, again, same equation, right? Fg dot x. Now, let's imagine the ball being over here. The force of gravity is still acting downwards, but my displacement is now going horizontally. And so cos, now my angle is going to be 90 degrees, right? So that becomes Fg x cos of 90. And we know the cos of 90 is 0. So that part there is going to be equal to 0. So work by gravity in the second leg of the journey is equal to 0. Work done by gravity in the third leg of the journey is going to be, again, Fg dot product with the displacement. Now, in this case, when the ball is over here, force of gravity is now parallel to the displacement. And so what that tells me then is it's going to be cos of 0, which is 1. So that gives me mgx. Right? So the work done by gravity in this third part of the journey is mgx. And then by similar logic to number 2, work done by gravity in the fourth leg of the journey, so like going across here, is going to also be equal to 0. And so if I add up all the work done by gravity here, so if I go work 1 plus work 2 plus work 3 plus work number 4, you are going to see that that's going to equal to minus mgx, plus work number 2 is 0, plus work number 3, mgx, and then plus work number 4, which is also going to be equal to 0, oops, plus 0, and that's just going to be, so minus mgx plus mgx becomes 0, so you get 0 plus 0 plus 0, which is 0. So we see that work done by gravity, right, in this loop here is equal to 0, which satisfies our condition, right? The work done by a conservative force on an object moving through any closed path, right? Closed path equals 0. And so that's why we can say that gravity or gravitational force is a conservative force. Okay, so that's proven. Now we've also done, we have shown in previous video, right, that the other method of a ball going up straight versus a ball going up the ramp, and or like going up the staircase, for example, right? And we saw that all of these, the work are pretty much equivalent, right? So we see that yes, it is path independent. Sorry, the work done by gravity is path independence. It's only dependent on the position only. Right. So I'm just showing you. So this is another way to prove that gravity is a conservative force. Another way, again, my preferred way, is making a closed path or a closed loop. Okay, so that's fine. Now, next slide. And let me just check to make sure that I have covered everything here that I need to. Yep, doesn't depend on the path taken. Great. Yeah, great. Okay. Next one. Now I'm going to show that friction is a non-conservative force. I want you to try to do this one yourself first. See if you can manage to do it. And then after that, unpause the video and come back. Okay. Same method. I am going to just I think again because it's easier. Let's say I have a box. Now I'm going to do a top bird's eye view from the top, right? So I have an object. I'm just going to push it across the floor. The object is going to go this way, and then it's going to stop here. It's going to then go this way, and then it's going to stop here, and it's going to come down here. It's going to stop, and then it's going to go back to the original position. Okay, and then this is like all the same length. So let's just call this the first leg. Again, x1, x2, x3, and x number 4. Okay, I'm going to now draw the boxes in different length, different path here. So we can kind of do some force analysis. So this is when the box is on leg 1. This is where the force is in the second leg of the journey. This one is when it's on the x3, and then this one over here is when it's x4. Okay. Now, friction. What's so weird about, or what's not weird, but what's special about friction is that friction always opposes motion. So what does that mean? That means that the force of friction actually changes direction as I go around in the loop. So at this point here, because in x1, the box is going up, going, sure, this is my north up here, right? Going north. And so friction is going to act this way, right? Now, as the box is going east or going to the right, then friction is now going to go this way. As the box is being pushed down south, right, now friction is going to act this way. And then as the box is being pushed to the left or to the west, back to the original position, friction is now going to go this way. So you can see that friction is always opposing motion. And so now let's try to calculate the, I guess, the amount of total work done by friction. So we're going to call this total work by friction. Okay, and that's going to be equal to work done by friction on the first one, plus the work done by friction on the second one, plus the work done by friction on the third one, plus the work done by friction on the fourth one. Okay, so what is the work done by friction on the first leg of the journey? Well, that's just going to equal to negative F times x1, right? Because again, displacement is going forward, and then friction is going backwards, so the angle between them is 180 degrees. Cos of 180 is -1. That's why I have negative F friction times x1. And then what about the second leg of the journey, the second path, right, when it goes across? Well, in the gravity's case, because gravity always acts down and that thing goes across, it was 0. But in this case, friction is still opposing the motion. And so the angle between the displacement going this way and then friction is still 180 degrees. That means work number 2 is also equal to negative Fx, but now Fx2, right? Let's just say that, for simplicity's sake, all the x's are, the same. So it's a square loop, right? And then this logic, again, applies to the third one because displacement is down, force is going up. So again, 180 degrees. So now I have the third work, which is going to be minus Fx3. and then plus the fourth one, again, same logic, Fx4. Right, so you can see that the total work done by friction in the loop is no longer 0, because now it's actually equal to 4 times the work done by the one path, right? So it's actually non-zero and is bigger. And you can imagine that if if I change the path slightly, so let's say I elongate x3 to make it longer, then this value will go up, and so that means now the work done, the total work done by friction also goes up, right? So it's no longer just 4 times x1 or f of x1, right? It's now like a larger number, which means that friction is dependent on path. Is dependent on the path, right? Therefore, friction is a non-conservative force, right? You can also, again, make the argument that the sum of the work in a loop is not 0. So this here, not 0. Therefore, it's also a non-conservative force, right? So both argument is equivalent, and they essentially show that friction is a non-conservative force, okay? Now, the question then is, I'm talking about kinetic friction, by the way, in this case. Static friction is very similar to it. In this case, why is the work not the same between two paths? Where does the energy actually go? Because like by doing work, what I'm doing is I'm transferring energy to the object, right? So in this case, because friction is done against the object, and so it's opposing the object, but where does the energy go? Because like in this case, the box would be slowing down, right? So where does the energy actually go? Well, it's going into heat, right? So the work done by friction, is actually transferring into heat, right? Now, this heat energy is very difficult for us to recover to become useful again, because it's very high entropy energy. I won't go into entropy. You can search it up for yourself what entropy means. Okay. All right. Coolios. So to sum up, to conclude, I guess, because of how friction behaves, right? Because it's a non-conservative force, we can't actually define a potential energy for friction. What do I mean by that? Well, if you remember back to the video on potential energy, right, we said that potential energy, right, is energy associated. How do I spell associated? Associated with position, right? So potential energy is the energy associated with position or the configuration of the object. And so potential energy, or the idea of potential energy, really only makes sense if it can be stated uniquely for a given point. If there is, I guess you could say, if it purely depends on position. Purely depends on position, right? So potential energy only makes sense if it purely depends on the position. And so that means that different position or different location has a unique number of potential energy, right? So similar to gravitational potential energy. So if I have a ball here, it has a certain amount of potential energy. If the ball is here, you can have a certain amount of potential energy. It doesn't matter, which path I take to get there. The potential energy is just dependent on the position itself, right? It's not dependent on the path. And so this idea cannot be done with a non-conservative force. So potential energy, because it has to purely depend on the position, That therefore it cannot happen for non-conservative force. I'm just going to use NC for non-conservative, right? So non-conservative forces cannot have potential energy. It's impossible for us to define an idea of a potential energy for a non-conservative force because again, it depends on the path, it depends on so many things, right? Yeah. So what's the word? Vice versa, or like flip it the other way around, what that means is that in order for us to have potential energy, or potential energy can only be defined for conservative forces, right? Because non-conservative forces cannot have potential energy, and so flipping it around, that means that the only force that can have potential is your conservative force, right? And so that would mean things like these, right? So I can have a gravitational potential energy. I can have elastic potential energy. I can have electrical potential energy. I cannot have friction potential. I cannot have air resistance potential. I cannot have tension potential, right? So these ones I cannot have. So no potential energy for these ones, and yes, potential energy for these ones, right? So only conservative forces can have potential energy. Non-conservative forces cannot have potential energy. Or rather, not cannot have, but we cannot define potential energy for non-conservative forces. That's probably a better wording, right? Potential energy can only be defined for conservative forces. So yeah, so all the potential is always associated with the force, right? So yeah, potential is always associated with the force. Not all forces will have a potential energy, right? So there's no potential energy for friction, for example. Cool. So let's link this back to the work energy principle, right? So we've talked about work energy before. So with work energy, essentially, I have net work is equal to change in kinetic energy. Okay, that was my work energy relationship. Now I'm going to extend this work energy principle to now also include the potential energy. Okay, so in order for us to extend the work energy relationship to include potential energy, right? You can have to imagine with me. Imagine there are now several forces acting on an object. So if I have an object, right, there's a bunch of forces acting on it. It could be normal force, it could be force of gravity, it could be applied force, it could be friction force, etc. Right? I can essentially classify these forces into so it's either going to be a conservative force or a non-conservative force, right? So something like the applied force is going to be non-conservative, something like friction is non-conservative, something like gravity is going to be a conservative force, etc. Right? And so really, if I want to kind of simplify that slightly, I could say that the net work or the total work done on an object, yes, so we say that net work, we can calculate it using the sum of the net force times displacement. But again, as we said, right, all forces can be classified as either conservative or non-conservative. So I can break that down further. So I can say the net work on an object, right, is actually made up of work done by the conservative force and the work done by the non-conservative force. Okay. And so therefore, right now I can write this, work done, work net is equal to WC, work done by conservative, plus WNC, work done by non-conservative. Remember though that from last lesson, right, that a potential energy essentially, well, just then, we were just discussing just then, that conservative force, we can define potential for it, right? And a work done by conservative force can actually be written in terms of potential. So if you remember, work done by gravity from last video is actually equal to negative change in potential. right? Because again, remember, work done by an external force to lift up the object equals the change in potential. And we know that work done by gravity is opposite to the work done I do to lift up the object. So work done external is equal to negative work of gravity. And so from there, we can say that work done by gravity is just negative of the change in potential. Okay, so if you want to revisit that, you can go back to that concept. And so from the last video, so I can then actually generalize this a little bit more to say that actually work done by a conservative force like gravity is equal to negative the change in potential. Right, so now it's more generalized. So in this case before, it was the work done by gravity is negative work done, negative change in gravitational potential energy. But really, I can pretty much just generalize to say that any work done by a conservative force is just going to equal to negative change in the potential energy, whatever that potential might be, right? Could be gravitational, could be elastic, could be electrical, okay? Most of the time for us though, it's going to be gravitational. Okay. And so then I can substitute this back into my equation back here. So now I have, right, network is equal to the work done by a conservative force, which we just say is negative change in potential, but plus W work done by non-conservative force. Right? So I'm just substitute this in. But remember our work energy relationship over here. Right, so our work energy relationship over here says that the network is also equal to the change in kinetic energy. So if I change this to change in kinetic energy, I can see that the change in kinetic energy is equal to negative change in potential plus the work done by the non-conservative force. Or another way for us to write that is this. The non-conservative force, the work done by a non-conservative force is equal to the change in kinetic energy plus the change in potential energy. Now, you might be like, oh man, like that's really confusing. It might be, but I want you to kind of slow down and then work through it in your head, see if it makes sense. And this one is actually quite useful because it actually allows us to then to try to understand a few different situations, right? So for example, let's say I have an object, let's say, you know what, let me just get an extra page here. Right, let's say I have like an object down a ramp. Actually, you know what? I actually do have an object down the ramp here. Okay, without friction, right? So if it's only, if the only force acting on this is the force of gravity, right? And the normal force, okay? And then I can actually, you know what? I will leave this to you as an exercise. I will give you a different example because I think it's better that way. So let's pick a different example. Let's just say that I have an object dropping down. Okay, so I have an object here dropping down. The only force acting on this object is, of course, the force of gravity, right? We know that gravity is a conservative force. So we know that, you know, in this case, I have, you know, changing potential. Ignoring air resistance, now I have no work done by non-conservative force. That doesn't exist anymore because there's no air resistance, right? So no air resistance, no friction, right? And so then my equation actually simplifies, right? Because the work done by non-conservative force in this case is just equal to 0. So work done by non-conservative is 0 because there's none of them. So then in this this situation, I can simplify my work energy relationship to 0 is equal to change in kinetic energy plus change in potential energy. And so if I rearrange it, I can see that negative change in potential energy is going to equal to change in kinetic energy, which is what we got previous lesson, right? Essentially, as the ball drops down, all of that potential energy is going to be converted into the kinetic energy of the ball. So it makes sense. The useful bit about this formula or this equation in particular is that now I have a tool to work out how much work is being done by things like air resistance, right? Because I can go, well, if there is no air resistance, this is how much kinetic energy I'm expecting to have. If I then measure the kinetic energy of the ball and it's slightly less, so let's say the change in potential is like 200 joules, right? So my change in potential is 200 joules, but then my change in kinetic is only, let's say this thing here is only 150 joules, right? What that means is that there is some energy or some work that's being done by a non-conservative force, right? Because they're not equal, right? These things are not equal. And so I can then work out how much work is being done by the non-conservative force. So I just have to go, well, my work done by non-conservative force is just change in kinetic plus change in potential. So in this case, it is going to be equal to, let's see, change in kinetic is 150 joules. Change in potential is going to be 200 joules. And so my work done by non-conservative force, hang on, does that make sense? Give me a second. Sorry, missed a negative there. So let's say that, like, again, if the ball drops, right, the change in potential actually becomes a negative. So then I have to go minus 200 here. And so that means that I know that the work done by the air resistance, or the work done by the non-conservative force in total, has to equal to minus 50 joules, right? So air resistance is opposing the movement of the ball by 50 joules. Right, and so I think this now gives us a bit of a tool to start to work out like friction, and then I can use this to then work out how much is the force of the average force of air resistance, right? Because I know that the work done has to equal to force times displacement. So if I know how high it dropped, I can work out the average force over that whole length there, right? Because I have the work, I have the displacement, I can work out the average force, right? Not the exact force, because well, with something like air resistance, it changes with the speed, right? But I can work out the average force, which is really powerful, right? And I can actually use this for many other situations as well. So hopefully you can see how the work energy principle, the extended version, can be really, really useful, and it can definitely help us to solve many different problems. Again, if it's a bit confusing, that's okay. Go through the whole slide again. Pause at different parts of the video, try to wrap your head around it, and we'll try to use it in the next lesson as well. Yeah. But otherwise, I do want you to try this, right? So work out what is the work done by friction on an object down a ramp. See if you can try to form a mathematical equation for it. Okay. But other than that, I don't think I have much else to say for this video. Yeah, cool. I think that is it. So I'll see you in the next video. Bye-bye.